Hello, Assalamu alaikum. My name is Salman Zoha with metric number B0319104880. In this video, I am presenting assignment 3 for algorithm analysis. This video is based on decrease and conquer algorithm. So, this is our group member names. We have 4 group members, and now I'm gonna start with introduction. So, tree-based algorithms are used to visit any node or vertex which is a connected part. By iterating over all the vertices of the graph, you can do this quickly, executing the algorithm on each vertex that is already unvisited when checked, and this was called traversing a graph. Two algorithms are generally used for the traversal of a graph: depth first search and breadth first search. So in this assignment, we are going to talk about depth first search algorithm, and this is a basically decrease and conquer algorithm. Depth first search algorithm is an algorithm for searching a graph or tree data structure. This algorithm invented in 17th century as a technique for solving maze. It starts at a certain arbitrary vertex, heading down a branch as far as before backtracking. So the algorithm begins at a tree's root or top node and goes down a given branch or path as far as it can, then backtracks until an unexplored path is identified and then explores it. The algorithm does this until it was analyzed the whole graph. Basically, DFS algorithm uses a stack for searching. A vertex is pushed into the stack when it's reached for the first time. When it becomes a dead one, a vertex pops off the stack for the first time, where no neighboring unvisited vertex exists. For example, graph problems are analyzing network, mapping paths, scheduling, and finding spanning trees. Graph search algorithms such as depth first search are helpful to examine these contours. So now I'm gonna show you a real life example for depth first search. Depth first search is a typical manner in which many individuals solve problems such as maze naturally. First we pick a path, the maze. Let's choose a path according to some law that we lay out ahead of time for the sake of the example, and we follow it until we find a dead end or meet the maze endpoint. We backtrack and take an alternate path from a previous junction. If a given path doesn't work, and try that path. So basically, first we have to start at this point, then we go to this point and go to this point. When this junction is closed, then we backtrack and go to this path. Then we come to that path. When this junction is also closed, then we backtrack, and it will be continue until we reach the end of the maze. So this is the real life example for depth first search. Thank you.
Assalamu alaikum, this is Abdullah Dimizba. I'm going to explain DFS, depth first search algorithm now. So here we can see we have 5 vertices nodes here, 0, 1, 2, 3 and 4. We have we have visited and stack. So let's get started. The first we need to do is we need to take one adjacent vertex which is 0. It will go to the visited as an element, and the other elements will be in the stack. So basically the vertex we are taking will be in the visited, and the rest will be in the stack. So next we the previously we took 0 here. The next will be we took 0, so 1 is top element of the stack. So we will take the next one as which one will be top of the stack. So 1 is top of the stack, so we took 1, and since we already took 1, it will go to the visited, and the rest will be in the stack. Now we will take 2, since as I mentioned earlier that we need to take the top element of the stack. So 2 was the top and we took 2, and since we didn't add the element 4, so we are adding the element top of the stack. So the next step, we are taking top of the stack, which is 4 we took, and 3 is not yet visited. So once we visit 3, there is no stack available, all the elements are visited. So we have completed successfully depth first traversal of the graph. Thank you so much. Assalamu alaikum.
Assalamu alaikum. My name is Mirza Shahid Afridi and my metric number is B0319205005. So today I am going to talk about the depth first search algorithm, and here in this algorithm the main algorithm is actually this depth first search algorithm, which creates a depth first search tree particular for loop here. So traverses the vertices in such a way whichever vertex is marked as 0, it starts the depth first search from that vertex. So for example, suppose I have a graph like 2 subgraphs. So these 2 subgraphs are disjoint, so I have to can see the multiple trees getting created for this particular algorithm. So I have one graph with A, C, D, F, E, B, and another, and graph is G, H, I, J, which forms another graph, and these 2 subgraphs are disjoint. So let's see this particular algorithm works when we have this type of graphs. So what we'll do is, according to the algorithm, mark each vertex in as 0. So what I have done is I have marked all the vertices as 0 and set the count value is 0. For each vertex V in V, if V is marked with 0, we will start the DFS algorithm. So if any vertex marked with 0, I will pass the vertex A. So I will get into this function and A with our starting vertex. I will count the increment count plus 1, mark the initial vertex with count plus 1 is 1, and mark V with the count for each W in the V vertex adjacent to the V. If W is marked 0, so for this A have E, C and D. So let's pick C. So what we will do, C is marked as 0, so this condition is satisfied. So I will call the DFS of C. So which effectively means I have added C. So I have added C next to A. So I will call DFS on C. Then I will increment a count. So count plus 1 becomes 2, and mark V with the count. So you can see C becomes count of 2. Then for each vertex W, V adjacent to V. So any vertex with adjacent with C, so that has been marked as 0. So who are adjacent to C will be marked with 0. It's D and F. So what do? I choose one of them. So let's choose D. The DFS algorithm will be called again. So I will add D from C. So I will increment the counter. So it will become 3. So since I have chosen D, I have to mark D with the count value. And then I again check from D if D is marked with 0. So let's see what happens if we have D. So and then for D the only adjacent vertices is C and A. So we look here. So C is not marked with 0 and A is not marked with 0. So I will go ahead and so this for loop is done. So what do I do? So I have called DFS inside DFS. So it's a recursive call. So I will go back one step. So I will go back one step to C. I will check from the next vertex from C, which is marked as 0. So from C I have one vertex which is marked 0, so is F. So it will go to F. If F is marked at 0, I will call on DFS on F. The count gets incremented by 1. So I mark the vertex F with 4, and I will continue like this, and I will mark B, and B will be 5, and then I will go to E, and E will be 6. So I have reached the end, and these two adjacent can be reached. So I will add a dash to connect both of them. So from E I will go back to B, and the effect actually unrolls from the recursion, and it goes back to F, and it will goes back to C, and the cursors unroll and go back to like this, and it will go back to D, and then it will recurse back, roll back, and it will go back to A. So the DFS is done. DFS of G. So I will actually check this for loop, and which vertex is marked as 0. So we will see A is not marked as 0, neither the C, D, E, F, and B and E. So only vertex is marked next to S0, H, G. So what do? I will call DFS of D, and GFX will become the next static vertex, and I will count 7, and for each G in V adjacent to V. If G is marked 0, it will go back and call. So from G I search from G. There are two possibilities, H and J. I will choose H, and this particular step go ahead and continue like this until I get J, and the DFS algorithm completes. So that's all from me. Thank you.
Assalamualaikum. Once again, my name is Sadman Zoha and metric number is B031910480. So in this part, I am talking about complexity for depth first search, the time complexity and space complexity. So each vertex is visited once by depth first search and tested every edge in the graph once. DFS complexity is thus order of V plus E. So this means the graph is interpreted as a list of adjacencies. Complexity analysis. So the time complexity is order of v plus e, where v is the number of vertices and e is the number of edges in the graph. Space complexity is order of v, since an extra visited array is needed of size v. So this is all about the time complexity and the space complexity of depth first search. Thank you.
Hello, assalamu alaikum. My name is Nafis Ahmed. My metric number is B0319104881. Today I am going to compare with an algorithm which is better than DFS. So let's start. We think breadth first search BFS algorithm is better than depth first search DFS algorithm. Breadth first search and then depth first search algorithm both are decrease and conquer technique. Visits graph vertex by traveling over all the neighbors of the last vertex visited, and BFS uses a queue instead of a stack. Breadth first search is less space efficient than depth first search, since BFS retains the entire border priority queue, while DFS maintains a few points at each stage. DFS is a safer choice than BFS if it is understood that an answer is likely to be short deep within a tree. BFS is helpful because the depth of the tree will differ or if a single response is expected. The shortest path to a tree, for example, the whole tree is to be traversed. A safer choice is DFS. An optimal response is always returned by BFS, but this is not guaranteed for DFS. Both algorithms' time complexity is the same. However, if the maximum height is less than the maximum number of nodes at a single stage. In the case of space complexity, DFS would be more space optimized than BFS or vice versa. Therefore, BFS performs best if the problem requires locating the closest neighbor or the shortest path. As in the case of DFS, leaf nodes are first visited. So, because of these reasons, we suggest that BFS algorithm is better than DFS algorithm.